It's time now to apply our knowledge of differential equations to the real world. In many applications, the rate of change of a variable y is proportional to the value of y itself. So if y is a function of time, which it will be in these real world situations, then the proportion can be written as the following differential equation. We can state that the derivative of y with respect to time is going to be equal to k times y. So the derivative of y with respect to time is the rate of change of y, whatever y may be. It could represent a financial situation, a population, the amount of a particular isotope left of an atom, many other things. So many different things that we can talk about. And so what we're saying here is that the rate of change of y is proportional to y. What k represents is that proportionality constant. This means that the ratio between the rate of change of y and y itself is constant. The ratio between them is constant. And that constant ratio is k. And so that identifies the proportion between y and its derivative. So here's a theorem your textbook might present. If y is a differentiable function of time such that y is greater than 0 and the derivative of y is equal to k times y for some constant k, then y equals c multiplied by e raised to the power of k times time. So c is the initial value of y, and k is the proportionality constant. Exponential growth occurs when k is greater than 0, and exponential decay occurs when k is less than 0. So let's go ahead and backtrack for a second. The reason y needs to be greater than 0 is because we're dealing with amounts, like population, money, other things. And we cannot have a negative amount in these particular situations. If we think about the graph of e raised to the power of kx, so not the theorem presented here, but let's say we were just looking at e raised to the kx. It'll be a growth function if k happens to be greater than 0, as shown here. If k is less than 0, then we can say k is some negative value. And so I'll just say we're using negative k to represent that. So we'll have y equals, let's say, e to the negative kt. This is equal to 1 over e to the kt, which will show as a decaying graph, as shown here. So again, k being greater than 0 means we're dealing with an exponential growth function, and k being less than 0 means that we're dealing with an exponential decay function. So let me prove that this theorem holds true. I'm going to go ahead and solve for the general solution of dy over dt equals ky. The way I'm going to begin is with any differential equation. We're going to separate our variables. So this dy, I'm going to leave it on the left. dt, I'm going to try to get that on the right side. And the way we can do that is by multiplying both sides by dt. In doing so, we'll have the differential of y equals ky multiplied by the differential of time. From here, we can go ahead and divide both sides by y in order to receive our complete separation of variables. So this means that we'll have 1 over y dy equals k dt. From here, we can go ahead and just integrate. We'll integrate both sides since both sides have their integrand and what they're integrating with respect to as the same variable. Since k is a constant, hey, that's like k times t to the 0 power. So we can think about it that way. So what this means is that when we take the integral, we'll have, well, this will be the natural log of the absolute value of y plus c1. The reason I'm including c1 is because we're going to have another constant on the right. So upon integrating this side, we'll have kt plus c2. And quick note that we want to make. This absolute value of y actually doesn't even need to be an absolute value symbol. It can simply be the natural log of y. The reason for this is because we stated earlier, y needs to be greater than 0 because it represents an amount. So moving forward, as we saw previously and many other times, when we move constants together, if we add constants together, multiply them, raise a constant to a constant power, they are still constants. So what I'm going to do is I'm going to go ahead and move this c1 over to the right side, leaving me with the natural log of y equals kt plus c2 minus c1. Remember, if we have c2 minus c1, this is still a constant. And so I'm going to state that this is going to be another constant. I'm going to say this is my third constant. And the reason I'm using a third constant is because another one's going to pop up soon. So we have kt plus our third constant. Now let me go ahead and just erase this over here so I have more space to work with. Now, to finish this thing off, what I'm going to do is I'm going to raise each side. So I'm going to do e to the power of ln and then e to the power of all of this. So that'll leave me with e to the power of ln equals e raised to the power of kt plus my third constant. Now, remember, using our properties of logarithms, note that if we have a base raised to a logarithm whose base of that logarithm is the same as our base, the argument is the answer. And so this can be reduced to y. On the right side, what we want to notice is that if we had, let's say, x squared plus x cubed, or not plus, if we have x squared multiplied by x cubed, this will give us x raised to the 2 plus 3 power. I'm going to use the converse of this property to split this up into two terms like we see here. So e raised to the power of kt plus our third constant is the same as e raised to the kt power multiplied by e raised to the third constant power. This is where I'm going to go ahead and eliminate the need for that constant anymore, because e raised to the c3 power, e is a constant, c is a constant raised to a constant power, I'm going to let this equal c. So what this means, to finalize, we'll have y equals e raised to the kt power multiplied by c, and we can go ahead and rewrite this as c multiplied by e to the kt power. So what this means is that all solutions of dy dt equals ky, they're all of the form y equals c times e raised to the kt power. And we can prove this by performing the derivative on the general solution. And here it is. We would begin by computing the derivative with respect to time of both sides. Next, notice the derivative of y with respect to time will be represented with dy over dt. Next, the right side. I'm going to begin with the constant because we have the constant times a function, and so the derivative of a constant times a function is a constant times the derivative of that function. And for a quick little review, remember, if we're computing the derivative with respect to anything, let's go ahead and use time for this scenario. The derivative with respect to time of e raised to some function's power, I'm going to say u, this will be equal to e to the u multiplied by the natural log of e, which will reduce to 1, so it's not necessary to show, and then we'll multiply by the derivative of u with respect to time. So what this means is that we'll have c multiplied by e raised to the kt power multiplied by the natural log of e, which would be 1, and then multiplied by the derivative of kt. That would be k. All we need to notice at this point is that, hey, c times e to the kt, guess what? That's y. That is y. And so we can go ahead and replace that, stating that dy dt over here is equal to, we can replace that with y multiplied by k, or k times y. Either way. And so I hope by now we agree with what's being presented so far. Let's tackle an example problem to try to solidify this. The rate of change of y is proportional to y. When t equals 0, y equals 2. And when t equals 2, y equals 4. What is the value of y when t equals 3? Here's how we can tackle it. First, notice from the very beginning, they stated that the rate of change of y is proportional to y. That should be an automatic indicator that we should look to use the following equation. We should look to use y equals our initial condition multiplied by e raised to the kt power. And the reason I specified c as that initial condition, because remember earlier, that theorem, C is the initial condition. In this particular situation, they give us that when t equals 0, y equals 2. I'm going to prove that C equals 2 because of this. We can go ahead and just set everything the way it's supposed to be. So y equals 2, t equals 0. So we'll have 2 equals C multiplied by e raised to the k times 0 power. Well, anything times 0, remember, that's 0. E raised to the 0 power, or anything raised to the 0 power, that is 1. And in order to avoid being redundant, that's gone. Oh, there it is. 2 equals C, C equals 2, same thing. We are good. Now, up next, what we can do is we can go ahead and rewrite. So we'll have y equals 2e raised to the kt power. However, even though we solve for the initial condition, we still can't solve for y when t is equal to 3. It's because we still have to solve for that proportionality constant. Here's how we can do it. We're also told that when t equals 2, y equals 4. Using that condition, I can go ahead and further solve for k. So by substituting y equals 4 and t equals 2, I'll receive the following: 2e raised to the k times 2 power, or 2k. From here, we can easily now solve for k since it's one variable inside of a one equation. One equation and one variable means we can solve for that variable. So we can go ahead and begin by dividing both sides by 2, leaving us with 2 equals e raised to the 2k power. From here, I notice that this is in exponential form. Our equation is in exponential form. I want to go ahead and convert this to the logarithmic form. So the e, that is our base, 2 will be our argument, this 2k is the exponent. So in doing so, we can rewrite it as a logarithm with a base of e. And remember, a logarithm with a base of e, that is the same as the natural log. So we'll have the natural log of 2 equals 2k. If I lost you there for a second, don't worry. Another thing we can do from over here is we can go ahead and take the natural log of both sides, leaving us with the natural log of 2 equals the natural log of e raised to the 2k power. Upon using our little properties of logarithms, we can go ahead and take this 2k, make it a coefficient in front of the natural log of e, making it the natural log of 2 equals 2k multiplied by the natural log of e. And we should know by now that the natural log of e is 1, just like that. And so we can go ahead and remove that to avoid being redundant. Either way, we'll end up with the same answer. So let me go ahead and erase this. That way I can go ahead and proceed. Now, to solve for k, all we got to do here is just divide both sides by 2. And we're good. So this means that k is equal to the natural log of 2 divided by 2. And upon using my calculator, this is approximately equal to 0.3466. And I'll go ahead and leave it at 4 decimal places. So in order to solve now, we've solved for k, we solved for c. All we got to do is plug in that t value that we want. We want to know what y's value is when t is equal to 3. So in order to finalize, we just need to have y, set it equal to 2e raised to the power of kt. K we found was the natural log of 2 divided by 2, and the time that we're looking at is 3 seconds. From here, all we got to do is go ahead, plug and chug. And once we do, we'll receive the final answer, y equals 5.6569. And there it is. That is the amount that y is equal to at 3 seconds. And if we're in AP calculus, remember to always round to 3 decimal places. So we can go ahead and state that this is approximately 5.657. That will be the amount of y. We're not really given any units for y, whether it was money or whatever it may be. So we'll just say y is approximately equal to 5.657 at t equals 3. And so I hope you found this overview video interesting, as I'll be tackling all real-world situations that you may encounter in my preceding example videos. Those situations will include radioactive decay, population growth and decay, exponential growth and decay of sales, Newton's law of cooling, and more. So let us know if there's a particular situation you feel isn't covered, and we'll get right on it. Until that happens, the ball's on your side of the court. Time to master calculus. Have fun.